Hello class. So the research project that I chose to do was about acidity, the Cherry Coca Cola, and dental erosion. So could the acidity of a Cherry Coca Cola contribute to dental erosion? Let's see. So what's the aim of my research project? So the purpose was to determine the acidity of soda pop, in my case was the Cherry Coca Cola, by measuring its pH and then performing a titration. And we will discover what this looks like. And also, we wanted to analyze if there is a relationship between the acidity of soda pops and dental erosion. So let's discover what's the science behind this experiment. So the first question is, what makes sodas acidic? And the answer is the acids. In this case of the cherry coke is this phosphoric acid. So you can see in the soda can, in the list of ingredients, there it's write down phosphoric acid. And those acids are added into the soda to improve flavor, reduce growth of bacteria and fungi, because this acidic environment is a hard condition environment to them to grow and live, and also to improve shelf life. Another thing is the carbon dioxide present in the soda that reacts with water, and this reaction forms carbonic acid, which is another type of acid present in the soda and also contributes to acidity, but it's temporary. So because of this, we want to calculate the real acidity in the experiment. So the soda was decarbonated first, and after a titration was performed. And what is a titration? It's a method used to determine the concentration of a substance in a solution by reacting with a solution of no concentration. In this case of this experiment, the acid, that is the soda, is neutralized by the base, that is the sodium hydroxide, that is the solution of no concentration, because we know the molarity. And the second part is about the dental effects. So, enamel damage can be caused by different factors. Here in this figure from the source 2, you have some of those factors. So, cellular pH, exposure number, wrong eating habits, exposure time, and the pH of carbonated soft drinks. That is the case of the sodas. And all of these can cause the tooth decay. And so the carbonated drinks are just one of them. You can see here. However, the junction of bad oral hygiene habits and the constant injection of soda can cause a higher risk of erosion of dental tissues. Also, the critical pH value considered for enamel dissolution is 5.5. And according to a study that measured the pH of 379 sodas from the United States and evaluated their erosive potential, the Cherry Coke had a pH of 2.38 and was considered extremely erosive. That according to this study, the sodas that was extremely erosive have a pH less than 3.0. Let's go to the experiment. So that is a list of all the materials and chemicals that I used. So Cherry Coca Cola, we use approximately 700 millimeters, a hot plate, a magnetic stirring bar, 1 liter beaker, pH meter, burette clamp, and retort stand, distilled water, graduated cylinder, safety equipment like goggles, gloves, and apron, 150 millimeters, and sodium hydroxide solution with a molarity of 0.1375, and also a funnel. So let's describe the method. The first step is to prepare the soda sample, so it's the decarbonation that I talked earlier. So to do that, we heat the soda on a hot plate for approximately 1 hour while stirring. And what is the purpose of doing that? So the purpose is to remove all the carbon dioxide, which forms the carbonic acid that I talked earlier, because we only want to analyze the soda's real acids, that in this case is the phosphoric acid. The second step is to set up the pH measurement. So you grab the pH meter and measure and record the initial pH of the gaseous soda. The third step is to prepare the titration. So first, use the sodium hydroxide with a concentration of 0.1375 as a tritant, the base. Place 7 milliliters of the soda in a clean 150 milliliters beaker and add a magnetic stir bar and place it on a hot plate to start to stir during the titration. The next step is to perform the titration. So in this step, you need a lot of patience and add the sodium hydroxide very slowly in small amounts, drops or zero point 0.5 to 1 millimeter at a time. After each addition, you record the pH and the volume of the sodium hydroxide. And you have to continue adding it until the pH stops changing significantly and the solution becomes basic, that is around a pH of 10 to 11. And the last step is to identify the neutralization point. The point where the pH changes slowly indicates that the soda acid have been completely neutralized. So that's the neutralization point. And at this point, the moles of the sodium hydroxide added is equal to the moles of acid in the soda sample. And this is a very important thing to the observations and calculations that we will be seeing in this presentation. And you repeat all these steps for each trial. So as I was describing the method, I said to you to record all the pH values and the volume of the sodium hydroxide. And this is a table of my values of the trial 1. And using those values, I made this graph so you can see the titration curve and also the equivalence point that it's here where it indicates, and I'm going to explain what this means, the equivalence point and those values. This is the values of my second trial, and that is the table that I made with the values of the trial 2. You can see that both graphs are very similar, and I'm going to analyze and see how this is a good thing. So let's go for the data and observations of our experiment. So those values that I show you on the graphs means that 4.25 to 4.60 millimeters of sodium hydroxide were required to neutralize the acids in 7 millimeters soda sample. And using all of those values and the relationship of the equivalence point, the neutralization point, that the moles of the sodium hydroxide is equal to the moles of the acid, we can calculate the amount of acid in the soda. So the step 1 is to calculate the moles of the sodium hydroxide at equivalence point. So I did the calculations for both trials. You can see here the moles. After I calculated the average using both values that we found on the previous calculation, and that is the quantity of moles of acid per 7 milliliters of soda. And the step 3 is to calculate the concentration of acid in the soda. And we use the formula for the molarity. So acid molarity is the moles divided by the volume. So here's the moles that we found here divided by the volume that we used in which trial, that was 70 millimeters converting to liters. And here we discovered our concentration of the acid in the soda. Let's analyze all the values that we discovered. So, in the experiment, the average initial pH of the soda was 1.99, which is very acidic, and it is approximately 100 times more acidic than the critical pH value considered for an ml dissolution that we see before, that was 5.5. Also, the pH of soda increases slowly at first as the sodium hydroxide was added, but around 4.25 to 4.60 millimeters of it, there was a sharp rise in the pH that we saw on the graph. And this sudden increase shows the equivalence point, and the point that I show you was that point, the equivalence point, meaning that all the major acids in the soda, that in this case is sulfuric acid, had been neutralized. Also, the 0.08692 concentration calculated tell us how much phosphoric acid is actually dissolved in the soda. And this value is significant because even at around 0.08, phosphoric acid contributes to a large number of hydrogen ions, bringing the soda's pH down to around 2, which is extremely acidic for a drink. So the acid is strong enough to damage enamel, lower oral pH, and contributes to dental erosion when consumed frequently. So, as a conclusion, these experiments successfully show the relationship between the acidity of sodas with dental erosion and enamel damage. The values of the average initial pH of 1.99 and acid concentration of 0.008692 contributed and confirmed that soft drinks contain enough acid and contribute to enamel damage. Also, the two trials and the values that I got on both trials and the graphs are very similar to each other, and they have the same conclusions, so they contribute to each other. So all of that data is very important because the consumption of carbonated drinks has grown significantly from children to adults, and it's popular in people's daily routine, and everyone have sodas in their homes and have access on in a very simple way, and often water is replaced by those drinks. And this is alarming because, as we saw in this experiment and in other studies that we use in this project, sodas have erosive characteristic and can affect oral health. That is the bibliography that I used, all the studies that I used in this research project. So, what could be improved and what more research could be done? So, perform more trials to have more data to work on and compare. Even though both trials that I performed were very similar and they have the same conclusions, it is always important to have more data to have more accuracy in your findings. Also, compare diet soda versus regular, so see if there's a difference related to acidity, compare with different brands or types of soda within the same brand, measured Emanuel laws by in vitro simulation, so by immersing teeth or eggshells could be really interesting, and perform analysis of the sugar content in soda and see if there is also a relationship between the sugar and dental erosion, not only the acidity. I would like to thank firstly Professor Sharma for guidance in this project, for all the support, and the chemistry lab staff of Arlington College for providing all the materials and chemicals that we used during this experiment, and for my classmates for assisting during the experiment. And thank you so much for watching.